All right, so this video is going to be short and sweet. It's just going to be me covering the properties of the integral. And since the integral is very closely related to the derivative, right, we saw in the very first video, I had done an example where I had something like x cubed, and on the one side, we took the derivative with respect to x, and we got 3x squared. Now on the other side, I can finally kind of put this symbol that we have a little bit more context behind, and I could write the integral symbol. And to be more complete, it'd be the integral of 3x squared dx. And that gets me back to x cubed, but then we have to throw in this this plus c bit here. The most important thing is that the integral is closely related to the derivative, and as such, it inherits very similar properties of it. So the first such property is that if I have the integral of some function, call it f of x dx, and I want to add it to the integral of another function, dx like so, this is the same thing as if I had just done the integral of f of x plus g of x dx like so. Very similar to how derivatives work, right? Like if I have, for instance, like x cubed plus x squared, if I want to take the derivative of both of these simultaneously, right, or rather of the whole thing, I can kind of just, if you want to think about it, distribute in the derivative operator here, right? The derivative behaves in what we call a linear way. It's a linear operator, and all that means is I can take the derivative of the first thing on its own and then take the derivative of the second thing on its own, and then we just add kind of the answers together and we're good. So for example here, if I have the integral of x cubed dx and I were to add it to the integral of x squared dx, then I would simply, that's the same thing as just doing the integral of x cubed plus x squared dx. So it goes both ways. If I were to start here, I could just do them each individually. And this answer would just be x to the fourth over 4 plus x cubed over 3. And then we tack on that plus c, and there's our answer. And we could always check our answer, of course, by taking the derivative. So it works the same for addition, and it's going to work the same for subtraction. So very much so, just like how the derivative works. If we subtract two integrals, we could just subtract the two functions instead, and we would get the same thing. One other interesting property that the derivative had was if we had something like, for instance, let's say I said, find the derivative of 7 sine of x, what we could do is we could take this coefficient here, and we could always pull it out and put it in the front. Right, I could always write this as 7 times the derivative of sine of x, right? We don't ever really write this out, but the point is that they both just mean that the answer is going to be 7 cosine of x. So we get to kind of ignore that coefficient for a second, take the derivative, and then we're good to go. So we can pull out these coefficients. And so in the very same way, integrals work the same way. And so, for example, if we have the integral of, say, 7 cosine of x dx, I can write this. It's the same thing to put the 7 on the outside and then have, the integral of cosine of x dx, and then be like, I can pull out the 7, no problem, and the antiderivative of cosine is just sine. So this is going to be 7 sine of x plus c. Now, this is totally perfect. This is fine. But one place where students generally have one of their first questions is at this part where they say, well, the antiderivative of this is sine of x plus c. So shouldn't I write my answer then with this 7, right? Doesn't PEMDAS work? And the way it'd be 7 multiplied by sine of x plus c, which is therefore equal to 7 sine of x plus 7c. And I would say, yeah, this is totally perfect, 100,000% correct. And my answer to you is that this 7c and this c over here are the same thing. And what I mean by that is remember that the whole point of tacking on this plus c at the end was just the fact that if I take the derivative, this c could be any constant just slapped on at the end, because the derivative is still going to match cosine of x. And so if I were to, go this way and do 7 multiplied by sine of x plus c, and then get here, last time I checked, 7 multiplied by some random constant is still just some random constant. And if you wanted, you could call it a different letter, d. I just decided to just call it c again. So just to restate one more thing, this particular c and this c are not the same c, right? They're not the same c. So it may be more appropriate to rewrite this as plus d if that makes you feel a little bit more warm and fuzzy. But mathematicians and people who work in calculus in general, we kind of abuse the notation, which is we just say, look, 7 times c last time I checked is still just some constant. So they just say, well, let's label this, you can call it if you want, new c, right? But we just use c to represent some general constant, so we don't ever have to really worry about it. So again, maybe if that's a little strange, you want to see one more example. If I had the integral of 3e to the x dx, then this would be, well, I can pull the 3 out, integral of e to the x dx. And there's 2 ways you can think about this. You can just say, well, the antiderivative of e to the x is just e to the x, so the answer is going to be 3e to the x plus c. Or you could go the other way where you say, well, this antiderivative here is e to the x plus c, like so, and then there's the 3 from earlier, and so my answer should be 3e to the x plus 3c. But again, this 3c is just some constant, right? It's just another random constant, and so we just package it together and say, let's just call it new mega c if you want, right? It doesn't really matter. It's just there as a placeholder to indicate that there's some value that could be there, because when we take the derivative, it's going to match up over here. Now, things that we can't do with the integral, okay? So just like with the derivative, right? If we had f multiplied by g, or we had f divided by g, right? We didn't just say that the derivative of this, right? If I just do this, it's not equal to just the derivative of f with respect to x multiplied by the derivative of g with respect to x, right? This is not what it equals, right? This requires more careful handling, right? This one, for instance, required the product rule, okay? And the next one required the quotient rule. And so very similarly, right, it is not true, right, that the integral, if I have 2 functions, f of x multiplied by g of x dx, this is not equal to the integral of f of x dx multiplied by the integral of g of x dx. This is not equal. Same thing with a quotient, same thing if we were doing division. And the reason why, just to kind of, again, just to help you relate it, is we could not do this with derivatives, so it should not be so easy with integrals. That's the easiest way to kind of think about it. So if it ever looked a little strange with derivatives, so for instance, like the integral of the natural log of x, right? You're asking yourself, well, what function has a derivative that is the natural log? And the answer is we don't know what that is, right? When we dealt with the natural log before, it required some careful handling. If you wanted to see an example of where, for instance, this fails, just consider, like, let's pretend I have the integral of x multiplied by x, right, dx, okay? Right, so on the one hand, this is just the integral of x squared dx, which we should get x cubed over 3 plus c, right? That's what we should get. But if you try and you think that this is the integral of x dx, and then that you're going to multiply that by the integral of the other x dx, well, this answer is going to give you x squared over 2 plus c. This answer over here is going to give you x squared over 2 plus c. Right? Hopefully you can kind of see that if I take these answers and I multiply them together, I'd have to do foiling, we'd have to distribute this properly. We're not going to get this answer, right? Like the dead giveaway is the fact I'm going to have an x squared multiplied by an x squared, which is going to give me an x to the fourth. And that just right off the bat is like your big red flag that clearly these are not the same. So we will learn in this class. Remember, I keep pointing out that the purpose of this class largely is to figure out how to think about integrals, how to solve the integrals, how to basically do antiderivatives. And it's going to require a bit more of a delicate touch when we are handling problems like this, but we are going to learn how to handle them in the future. So that's going to do it for this particular video. Just a couple quick things about the properties of integrals, being able to add and subtract them, to be able to pull out constants, which you may see this second rule is basically saying that the integral of c multiplied by some function dx is equal to, you can just pull that coefficient out and you get that. That's how you may see it shorthanded. But you don't get to do any more secret cheating cuts. That's it. That's as good as it gets. So those are our very simple rules, okay? So that's going to do it for this video. And in the next one, as I originally promised in the previous one, we're going to start talking about how to evaluate those definite integrals.